Good day everyone! Today we will explore a crucial concepts in thermodynamics, control volume analysis and its role in steady state and unsteady state conditions. In thermodynamics, understanding how mass and energy flow across system boundaries is essential. Many engineering applications involve open systems where energy and matter interact continuously. Our focus today is on fundamental concept on control volume analysis, how thermodynamics principles apply to steady state and unsteady state systems, real application that demonstrate the significance of control volume analysis. A control volume is a defined region in space where mass and energy can enter and exit. Unlike flow systems, which do not allow mass transfer, control volumes are essential for analyzing fluid flow, power cycles, and thermal processes. There are few key features of control volumes. First is mass and energy flow through boundaries. Unlike flow systems, control volumes allow for continuous interaction. Flexible boundaries. The system boundary may be fixed or moving depending on the application. Ideal for engineering applications, used in devices such as boilers, turbines, compressors, heat exchangers, and jet engines. For examples, as steam turbine, high-pressure steam enters, expand while performing work, and then exit at a low-pressure steam. Second, a gas compressor, air enters, is compressed and leave at a higher pressure. The control surface is the boundary that separates the system from its surroundings. There are few types of control surfaces. First is the fixed control surface. Applies to stationary systems like boilers and heat exchangers. Number 2, moving control surface, used in dynamic systems like jet engines or rocket combustion chambers. Real or imaginary control surface. Physical boundaries exist in heat exchangers, while conceptual boundaries are used in airflow studies. Why is defining the control system important? Precise control surface selection ensures accurate application of mass, momentum, and energy conservation equation.
Good day everyone, I'm Diana and today we'll explore control volume analysis or CVA, a crucial concept in thermodynamics and fluid mechanics. CVA helps us understand how fluid behave within a defined space. What is control volume? Imagine drawing a box around a part of a system you want to study. This box is our control volume. It could be a section of pipe, an entire engine, or anything in between. We use CVA to analyze the fluid within this defined space. There are too many types of CVA, steady state and unsteady state. The key difference lies whether the fluid properties inside the control volume change over time. Now let's discuss first the steady state. In steady state, the properties inside our control volume remain constant. Think of a river flowing smoothly. The flow rate, pressure, and temperature are relatively consistent at any given point. The amount of flowing in equals the amount of flowing out. This makes the analysis much simpler. A good example is power plant steam turbine. Once it's running at full capacity, the steam flow, pressure, and temperature are relatively constant. Another example is a refrigerator. Maintaining a constant temperature, the refrigerant circulates, but the overall temperature inside stays stable. We can ignore short-term fluctuation and focus on the average behavior. Why it's simpler? Because nothing is changing rapidly with time. The equation for steady state are much simpler. They mainly focus on conservation of mass and energy. The mass flowing in must equal the mass flowing out, and the energy entering must equal the energy leaving. Now, we'll discuss the specific equation more later, presented by the next presenter. Now, let's look at unsteady state. Here, the properties inside our control volume change with time. Think of filling a bathtub. The water level changes constantly. Heating a cup of water in a microwave is a perfect example. The water's temperature increases over time but not at a constant rate. It's faster initially and slows down as it gets hotter. Charging battery is another example. The charge level and temperature change over time. Why it's more complex? Unsteady state analysis is more complex because we need to account for how properties change with time. The equation include time-dependent terms, making the calculations more challenging. Again, the detailed equation will be covered by the next presenter. Why unsteady state is more complex? Unsteady state analysis is more complex because we need to account for how properties change with time. The equation includes time-dependent terms, making calculation more challenging. Again, the detailed equation will be covered by the next presenter. To summarize, the steady state is simpler and used for systems with constant properties. Unsteady state is more complex and used for systems where properties change significantly over time. The choice depends on the system being analyzed. We've covered the basic concepts of steady state and unsteady state control volume analysis. Now, the next presenter will delve into the specific equation used for each type of analysis, providing a more mathematical understanding. That's all. Thank you.